Okay, so it looks like we're going to get started. I imagine a couple more might join us when they finish their lunch. So thank you very much for coming to this session. It's probably the least practically useful session you're going to attend in the entire conference, but I hope to make up for that by being interesting. If it's any help, there's a respite from Agile. There's nothing Agile or anything too funky in this talk. So what I'm going to be talking about is programming and how young people learn to program in schools and out of schools. So recently there's been a bit of a push, especially in the UK, to reintroduce computing into schools. So a subject that used to be called ICT has now become computing. It includes a fair amount of programming or algorithms and those kind of things. And it's now going to be mandatory come September for all students in UK schools from ages 5 up to 14. So there's a lot of sort of push towards computing and coding and things like that. There's sort of these movements, code.org in the US, a few other movements around Europe. And so I'm just going to look a bit today at what sort of things are they doing. So learning programming now is perhaps a bit of a different thing than when you guys learned programming, than when I learned programming. So I'm just going to talk through some of the systems that are available today, show you one that I'm involved in developing, and just sort of give you an idea of the kind of things that you can do nowadays if you're looking to learn to program. So there's a variety of different things for different age groups. So at the very youngest age, saying, oh, they're going to program from age 5 sounds like a sort of very bold step. But really it's more about getting them used to the concepts. And you can do a surprising amount of computing concepts without a computer. So there's various resources around things like CS Unplugged, which allows you to do exercises where the kids run around the room and sort of do stuff. There's one involving internet routing. So you set up bunch of tables in the room, and they sort of lay down, some tape and say you can only go from this table to that table. Here's a message. You've got to get it to the other side of the room. Off you go. So they sort of, do a little pass between the tables, and they say, nope, this table is not available anymore. This node has, dropped from the network. You're going to have to route around. And so just doing little sort of, playful exercises like that. You can get across the concepts, but you're not sitting there looking at the TCP/IP specification and sort of, baffling over that. One of my favorite ones is this thing called Jam Sandwich Bots, which is where this teacher stands at the front of the class, again, these are 6, 7-year-old kids, and says, okay, tell me how to make a sandwich. So they lay out on the table, they've got like the bread, the butter, like a knife and a plate. Say, how do you make the sandwich? And so then one of the kids says, well, put butter on the bread. So the teacher at the front takes the tub of butter, puts it on top of the loaf of bread and says, okay, what next? And like, no, you've got to take the bread out the wrapper. Like, okay, I'll take the bread out the wrapper, and then he just sort of chucks it on the floor. No, you've got to put it on the plate. And, just gradually refines it and gets it sort of more and more precise. Again, it's teaching concepts. There's no computer involved, but they are effectively learning how to program their teacher to make a jam sandwich. So there's a lot of fun stuff out there without a computer. The rest of the stuff I'm going to show you is involving a computer. So there's a system called Scratch, which I'm going to come back to later, which is incredibly popular, especially for sort of primary school age kids. And then later on, they tend to move on to sort of full programming languages, things like Python or Java, which is kind of where our interest comes in. So what I do is I work at the University of Kent, which is not far away, in the Computing Education Research Group. So officially my title is Research Fellow. What that really comes down to is I'm kind of a mix of a researcher and a software developer. So we do research into sort of how to learn to program, but we do it by actually building tools and trying to sort of take our philosophies on teaching and put them into a tool and put it out there so that people can actually use it and learn to program with it. So we're a very sort of practically oriented research group. So we develop a couple of educational tools called BlueJ, and I'm particularly going to be talking about Greenfoot today. So BlueJ, it tends to be used at a slightly older age. It's used a lot in the first year of university, and it's basically a sort of very trimmed down Java IDE. So you just program standard Java in it, but it just takes out a lot of the complexity that sort of full professional IDEs like Eclipse or NetBeans or Visual Studio or whatever might have. Just out of interest, does anyone here actually learn using BlueJ? Okay, we've got a couple in the room. You may well also have disliked it, but don't hold that against me. We get a lot of dislike sometimes for some of our tools. BlueJ in particular, first year of university, a lot of students come in knowing a lot of programming. They want to use Eclipse straight away because they've used it before, and BlueJ's like, oh, this is so dumbed down. The others haven't done any programming at all, and they're like finding it really, really difficult, and they're like, damn BlueJ, why is it telling me there's a code error, there's a syntax error, and stuff like that. So yeah, you sometimes get some pushback, but that's not always necessarily to do with the tool itself. Same goes for Greenfoot. Greenfoot is aimed at a younger age group. So essentially it's just a Java IDE, but the difference between BlueJ and Greenfoot is BlueJ is just sort of a plain IDE. Greenfoot actually has an integrated graphics, sound, and input sort of library that you can use straight away. So it just allows you to program Java, but to get started a lot faster doing things like games and simulations. And obviously I'll be talking you through in a sec some examples of that. So let's have a look at some. I'm going to be showing a few examples and doing a bit of coding in this talk. So let's start with a very classic example. Asteroids game. You guys are probably familiar with Asteroids. So sort of classic 2D arcade game. So this is Greenfoot. And so basically there's you can edit the code. So if I double click over here, then I can bring up, I've got a Java editor for the code, and I'll show you a bit more of that in a minute. But sort of literally built into the tool over here on the left-hand side, I've actually got, a graphics display. It's showing the sort of classes in my scenario. And if I click run here, then I can just play the game. So I've got a keyboard control here for running my little spaceship around. And if I hit the space bar, it's not very high contrast, but there is actually a sort of stream of bullets coming out that hit the asteroids and they split apart. And then I sort of run into something and get blown up. So any sort of, classic 2D games, especially sort of, arcade games, you can recreate in Greenfoot. And the idea is just to, by building it into the IDE, you've got it there already, you've got the libraries. It's sort of fairly easy to do. So there's a lot of games, and you can do various sort of games that you might imagine, but just to show you a couple of more educational examples, because of course that is our focus. So this one is not so much a game, more of a scientific simulation. So, but still using exactly the same system, exactly the same libraries underneath. So if I set this going and explain what's happening, this is simulation of sort of motion on a string, or sort of wave motion in physics. Each of these little red dots is actually a separate object, and the blue one on the end here is special. And each of the red dots just has a reference to each of its two neighbors, so the one on the left and the one on the right. And broadly speaking, we've got a couple of sort of coefficients for damping and things like that. Each dot just moves to the average position of its two neighbors. And then the blue one on the end, like I said, is special. It moves by itself. And so it turns out that just having the simple rule that you move to the average position of your two neighbors and one on the end that actually introduces some motion, you manage to sort of simulate motion on a string. So you can actually sort of investigate some interesting scientific effects, at a sort of suitable level for kind of secondary school, high school. By looking at the code and seeing how the behavior is, you can kind of poke around with it, change it, see what it does. So it's sort of a mixture of, sometimes we show games because, that's what gets kids really excited. This will perhaps get them a bit less excited. But still, you could use this in sort of other classes, physics classes or whatever, to investigate behavior. And just another example along those lines. This is an example of how ants forage for food, which we've created in Greenfoot. So I'm going to set it running, and then I'll just talk through what's going on here. So each of these two things here is an anthill, basically, and each of the little red dots running out is an ant. This green pile is a pile of food, and the ant's job is to go and grab all the food and bring it back to the nest. So you'll see that they've immediately found, say, this pile here, and they've quickly sort of formed a chain to empty it. The anthill is actually somewhere under there. As the ants are actually very good, if you watch them for a bit, at going out, finding all the food, and bringing it back to the nest. The way they do this, of course, ants don't communicate with each other directly. You don't just sort of command one ant to go over there and do that. Each of the ants is completely independent, and the only way they can communicate with each other is via pheromone, which we've visualized here as this sort of red splodgy stuff. Usually you wouldn't be able to see it, but sort of smell it instead. And so the way the ants behave is that they wander randomly. So these ants here are just wandering randomly, hoping to come across some food. But when one does, he then heads back to his home nest and drops pheromone as he goes. If another ant comes across the pheromone trail, they turn away from the nest and they head to the food, grab some, and come back. The more ants that join in with this, the more pheromone gets dropped, the more likely it is that other ants will notice, join in, form a chain, and bring all the food back. So they're sort of very good at bringing it back. So this is a fairly accurate sort of representation, roughly speaking, of how ants actually do forage for food. I particularly like this example because it's another example of, sort of showing scientific stuff in Greenfoot, but it's also kind of computing within computing. The ants are following a simple algorithm. Wander randomly, until I find food. When I find food, pick it up, take it back to the nest, drop pheromone. If I'm wandering randomly and I find pheromone, join in, follow the trail, grab the food, and do the same thing. So we've got this sort of algorithmic behavior that occurs in nature, but then we've actually embedded it in a Greenfoot scenario, so that, again, you can see what's happening. And here you can start modifying some of the parameters if you want to learn more about it. So, for example, the pheromone has a set lifetime. You can see that it disappears over time and vanishes. So you can see, oh, well, what happens if that I extend the life of the pheromone or shorten the life of the pheromone? It turns out there's actually a sweet spot in terms of the life of the pheromone. If you make it last too long, they all follow dead trails to food piles that have been exhausted. If you make it too short, you never get this behavior that they all join together and bring it back. So by experimenting and sort of altering things, you can actually sort of do some learning as well, and not just necessarily about the programming side. So that's a few examples of the sorts of scenarios that are possible in Greenfoot. So one thing that comes up a lot with these sort of systems is pedagogical design. So if you don't know the word pedagogy, Wikipedia tells me the science and art of education. You could obviously, doing education research, it comes up over and over again. But broadly, when we're designing this software, we not only have the sort of concerns that you normally would designing a piece of software. Obviously, you want it to be reliable, you want the user interface to be very sort of usable and easy, but you also want to encourage understanding via the interface. So you want the people who are using this to learn to program. Where in a standard user interface, you might just want to do as much as possible for the user and get, everything moving so smoothly that they barely need to do anything. That's not necessarily our aim here. We want to actually teach them programming. So we want to expose sort of useful concepts and things that they need to grasp sort of via the interface, while hiding away some of the detail that we don't want them to bother with. The reason we supply things like a graphics library built in is we don't want them to have to, write a graphics library from scratch as their first step. You want them to actually just be able to dive in, have a bit of fun, get started, start building something, but while they're doing it, be able to sort of actually learn and understand what's happening in their program, and sort of, the effects of their code as they go along. So to try and sort of demonstrate this and explain a bit to you, I'm just going to take you through a sort of abbreviated form of the workshops that we usually give to students. You'll be able to follow it, I imagine, fairly straightforwardly, being developers yourselves, and then just sort of provide a sort of director's commentary of, well, why do we do it like that? What are we trying to sort of teach them with this? What's the reasoning behind the way we do it? So with that in mind, I'll just switch across to Greenfoot. So we usually give the same workshop because it's different participants every time, but, same presenter, so I'm fairly used to giving this one by now. So here we've sort of got the Greenfoot interface. So you've sort of seen me using a bit of it already. We've got a few controls down here that actually sort of set the program running. We have our compile button over there for when we've modified the code. We've got a speed slider, but we don't have a whole sort of lot else here in the interface. So what we want to do is we're going to make a little game involving a crab that's going to run around. It's going to try eating some things and try not to get eaten by a predator that we're going to introduce a bit later. So the basics sort of with Greenfoot is essentially there's the running the scenario and then getting everything moving around, there's the editing the code, and there's also some interactions. So for example, if we want to make a new crab and put it in our scenario, we just right-click over there on crab, make a new instance, and just drop it into the world by clicking, and that just makes a crab, an instance of crab. It's sitting there in the world, and then if we wanted, we could hit run. Now, it doesn't do anything at the moment because we haven't written any code yet. They start off blank, so let's just write our first line of code. So by double-clicking over here on the class, we get up the code editor. Now you can see the sort of the syntax highlighting, so import is in red. That's the kind of classic syntax highlighting you get in all IDEs, keywords in a different color. We also have this sort of secondary highlighting in Greenfoot, which we call scope highlighting. So here, the area from sort of this end curly bracket to this start curly bracket and the header line, We recognize that's a class by parsing, just sort of the way you do for highlighting, but then we also draw an outline around it in green, and similarly each method gets an outline in yellow. So if I was to write another method here, then that gets yellow, and then any lines that I was to write inside it just sort of appear like that. So again, we're trying to do this to help out in the understanding of the curly brackets. One thing that we know from doing a lot of these workshops is curly brackets confuse students. Okay, they not only sort of what they mean, but also when students are editing, they just randomly go missing. So, they just sort of swipe a selection across a piece of code, hit delete, and all of a sudden they've got a syntax error and they didn't even know that they did it. So you can see here, because I've actually accidentally wiped out one of the curly brackets on the end there, the whole color of the background has changed. So it's a fairly visible difference when I've got the bracket in there to when I haven't. And so the idea is to try and sort of take their small mistakes and blow them up in a way so that they can sort of, see them more clearly. Oh, well, I've made a big change here. One character, in fact, in programming is potentially a massive change. But that's not always obvious to a beginner. Usually if you're writing a document in Word, leaving off a full stop, well, it's not the end of the world. But if you're programming, leaving out a curly bracket is potentially the end of the world. And not only is it an error, but it usually comes up with a pretty terrible error message. So for example, down the bottom there, reached end of file while parsing is the message that Java-C spits out if you haven't lined up your curly brackets. Now, if you're learning to program for the very first time, you don't know what parsing means, so that error message is totally incomprehensible. One of our research projects at the moment is to try and improve the quality of error messages so that they're more amenable to beginners. One difficulty is that error messages are usually written from the point of view of the compiler writer. So essentially, they've written this wonderful compiler, and they get down in this case statement to, this default statement, well, oh, bugger, there's an error. And they just sort of say, oh, well, what's happened here? Well, I've reached the end of the file, and I was parsing. So they just write, reached end of file while parsing. And from a user perspective, it doesn't matter. I don't care that, you've reached the end of the file while parsing. You need to give me better help than that. So compiler error messages are not really designed in a kind of user interface, user experience kind of way. They're just very, well, they're a programmer, they'll figure it out. So there's sort of different challenges for beginners who are learning to program than developers who are using the compiler. So if we continue with our workshop, whoops. So what we want to do, we've got our crab, so we want to now get something happening. So let's write a line of code that gets our crab moving across the screen. Okay, so there's a move method. So essentially the way our framework works is everything that lives in the world is an actor, inherits from the superclass actor. Actor comes with some methods already, move, turn, we'll see a few of those in a minute, that actually have some behavior. So to get the crab moving across, we just need to write them one line. So then we just put our crab in the world, hit run, and it runs across the screen. So that's very nice, and if we want to, we can even then make a few more of them, and they'll all run across the screen together. And as soon as you show this to teenagers, they can't stop until the entire screen is solid crab, and like they've brought the system to its knees. They're not happy until it's all stopped completely. So then you sort of drag them back to, okay, let's do some coding. So we've done this move command, and you can explain, okay, that 4 is how far to move. You challenge them to, make it go a bit faster, make it go a bit slower by adjusting number up or down. So there's a very similar command called turn, and so that will send it spinning round. So let's have a check on that. So that goes round and round, and again you can sort of, okay, try modifying that number. Can you get it turning in the opposite direction? Okay, and often, they get it. Okay, let's try -5, go in the other direction. A few get really fancy, 355, if they manage to figure out that it's degrees in there. I was once at a workshop where I said, okay, we've said turn 5. Can you figure out what that 5 means? And one guy there was like, I think it's degrees. It's not that funny US unit radians, is it? Like, okay. So the US is to blame for mathematics. So we've got our move, we've got our turn. That sets the crab running round. But really we want interactivity. Okay, it's not much fun if you just set off going by itself and you can't control it. It's no game if you're not involved. So what we do is then write some code. Okay, let's look for if the right key is pressed. So that just means the right arrow, and then we just take our turn out of there and put it into there. So let's get our crab going. So if we don't touch the keyboard, it should go straight. Okay, so it always moves. That was outside the if, but while I hold the right key down, I should then spin in circles. If I let go, if I hold it down, then I get that behavior. And from there, it's then sort of a small exercise to, okay, let's get left going in the opposite direction. And so then they figure out, that they want to sort of turn that. Let me just make that. Oh, wrong key. I was just going to make that a little bit bigger. There we go. That is a good question. Sorry, who asked that? Okay. I think now we do issue a runtime error if it's an unknown key. But it would be runtime rather than compiled. You could probably argue against our use of strings there for keys rather than constants or enums. I think Greenfoot predates Java 5, but I can't remember exactly. So now we put our crab in, and we've got full control. So it runs round, and when we press right, it goes right, and when we press left, it goes left. So that's all very fun. At this stage, we then introduce interactions between objects. So the crab's running around, but now we want an objective. We want something for the crab to eat, so we need to put some food in there for it. So we can then say, okay, well, everything in the world is an actor. We need a new kind of actor to be our food. Crabs aren't cannibals. They're not going to eat each other. Actually, they might be cannibals, but let's pretend they're not. So crabs aren't going to eat each other, so let's have some food in there for them to eat. So, okay. At this stage, I usually say, okay, let's have some worms for them to eat. But as soon as they notice that there's an image library, they can let their sort of imaginations run. They often come up with their own sort of scenario, because you can change the crab image to be what you want. So, you can have something like the crab becomes a hospital. The thing that they're eating is like a sick person, and actually it's an ambulance going around trying to pick up sick people. And then for others, it's like, I don't know, some terrible monster running around trying to, devour babies or something like that. But the nice thing is that it's the same behavior. Well, I'm just showing them really how to program entity A running around under keyboard control, making entity B disappear. And just through the graphics, they can come up with their own scenario and sort of have their own thing going on in their head, their own sort of scenario. But it's the same code. It's the same behavior. It just makes it a bit more theirs and makes it distinctive that they're not doing the same thing as the person sat next to them, at least not in their minds. As developers, you're used to, okay, the behavior is the key thing. But for them, just changing the images kind of makes it into a different scenario. So, okay, let's have our worm. And actually, our worm is going to be a sort of static target. We're not going to write any code for the worm. We're going to put the code for the eating into the crab. Of course, you can kind of do it either way. Whether the worm notices that the crab has eaten it or whether the crab actively eats the worm is actually a sort of software design decision. Who should have responsibility for the eating taking place. And so later on, you can sort of, once they've got the hang of it a bit more, you can talk through those kind of decisions. Early on, well, that doesn't mean anything to them. Okay, the crab is going to eat the worm, so that's fine. So then we have some collision detection that just looks to see if you're basically sort of have run into a particular class, and then you can tell it to remove any instances of that class that you're touching. So that code there, if is touching worm, remove the touching worm, will be enough. So now we can litter our sort of scenario with worms, and then drop the crab in. And when the crab runs around, every time it hits a worm, it will hoover it up. Okay, and you can also, if you want to, then add some sound onto that. So we usually supply a particular sound file already. Actually, I can't remember. I think is it eating? With it, so that if I then, and I have made a syntax error. Okay, so let's try that. Put our worms in, put our crabs in, turn my speakers on. Okay, so you get a nice slurping sound. One thing that we have included is actually a built-in sound recorder. So if they've got microphones, you can show that to them and they start burping into them and whatever, to make their sound effects to go with their game. But again, it's not programming, but it just helps them, sort of get into it a bit more. If they're having fun, then it makes the sort of learning a bit, less tedious. And that's sort of one of the principles behind the whole of Greenfoot, of course. You can learn programming with the command line, but isn't this more fun? That's sort of one of our key things. So then we can now we've got the crabs eating the worms, that's all fine, but it's a relatively easy game because there's no danger. So then you can add in a predator, so something like a lobster, to do that. Did I just say okay? I think, there we go. So then you could, if you wanted to, you could have the lobster keyboard controlled to be, a second player that runs after you. If they're pair programming, for example, that works out quite well if both of them can be playing the game. Or you can sort of instead have the lobster basically sort of, artificial intelligence in a very basic form. We've got a random number generator, so you can use that to make the lobster, run around and randomly sort of turn or sort of spin around. So it makes quite an effective predator. It's not particularly intelligent, but just being a bit unpredictable can make it tougher. I don't think I'll go too much into that, but essentially you can just borrow the appropriate bits of code from crab into lobster over here, so that the lobster eats the crab. And although it's not very effective, we'll just have our lobster sort of spinning roughly on the spot for us to avoid it. So if we now put a few lobsters in, put our crab in, put the worms in, then we've kind of got a game. So we run the crab round, it eats the worms, makes noises, and it gets eaten by the crab. And of course, you can make your own sound. So when the lobster eats the crab. So just there, I don't know how long that was, maybe 10 minutes or so. We tend to sort of spread it out with a little bit more over an hour, especially if we're sort of doing introductory workshops. But they really can make a game that they have actually actively written some code for, sort of relatively quickly and easily, and then they can go on from there and sort of extend it a bit further. One final feature that I just want to show, so you'll have noticed that each time I reset or compile, we basically blank the state, because of course when you're editing the code you may change the definition of a class, so we can't easily persist the class across sort of changes in the code state. We are just using standard Java, so essentially we just basically dump it, I think make a new class loader, load in the new versions of the classes, and start them again. But we do have a mechanism to stop it being quite so tedious with reinitializing. So essentially once you've done all this, we call this background area over here the world, so everything in it is an actor. We call the thing itself a world, and therefore if you want to save it, then clearly save the world was the only name that made any sense. So what this does, rather than try and be sort of too clever and do, for example, a serialization of the classes to some binary format, what we instead do is actually write some code that will do what you just did via the interface. So what we've got here is when I shift-clicked, so that's one of the shortcuts in Greenfoot, you select crab and then shift-click to make one. So then we just generate the code that makes a new crab, and this call adds it to the world. That's an X coordinate, that's a Y coordinate of wherever I happen to click. And then I made a few lobsters, so we generate that, and then we made a few worms as well. So the nice thing about this is now, as far as they're concerned, every time they hit compile, the saved state reappears again. But of course, it's really sort of recreating a new state with the same series of actions. But as long as they keep their classes with a no-argument constructor, the code will just continue to work just fine. And if they want to modify it, move any positions, they can then just do it by editing code. It also provides a nice illustration of how to do it. So it gives them a bit of guidance. Here's an example of how you sort of do some adding to the world that comes for free. So they can either just close it, just save the world, and that's all they need, or they can gain some understanding by looking at the code and seeing what it did. So that's a sort of taste of the kinds of things we do when we're introducing Greenfoot. I'm just going to talk through a few more of the details of the sort of why we do certain bits. So one thing that we try and do is we try and keep the interface very simple. Like I say, we're trying to be at the opposite end from professional tools. It's not about having 3 million options available. It's about not being too intimidating and just having what you sort of need to get started. So we've only got about four buttons down the bottom, a slider, and then you've got the sort of controls down the right and one more button. So it's sort of, keeps it fairly simple and clean, fairly approachable, we hope. It's a fairly easy development cycle, so especially once you've done that save the world bit, each time you make a change, you just need to hit compile and then hit run again. In fact, we've decided to catch up with everyone else. The compile button is going to go in the next major revision of Greenfoot. We'll just move to compiling all the time like most IDEs do. So what you'll need to do is once your code is free of errors, you just hit the run button to get started. So it'll be even shorter to try and do it. One consequence of our using a framework and using this graphics library. So essentially, you've got Greenfoot and it runs away, and each frame, it goes through all your actors and it calls the act method on them, so it's sort of a callback-based system. One consequence is that there's no main method. A lot of objection to teaching with Java, especially in the early days, you'd say, oh, have you considered Java? And they'd just look at you and say, public static void main string args. And you're like, oh, yeah, well, that is a bit annoying, isn't it? So you have to write this boilerplate. Every time you want us to teach Java, you have to say class something, and then you have to have public static void main, and they don't understand any of it. This is the first line they've written, and it's already not sort of meaning very much. So by sort of doing things this way, and BlueJ also avoids them having to write the main method, they just fill in the bit that's interesting in the middle of the program, and that's sort of one of our approaches. You don't have to write the whole thing from scratch. You just start with a bit that you can understand, and then you expand outwards from there. It just seems like a sensible way to do it. We also don't sort of operate with much console I/O. A classic way of teaching programming is you start on some sort of command line saying, print what is your age, taking in something, this is your age in dog years, or, examples like that. We think the visual example is much more interesting and just sort of, a lot easier to get into than trying to sort of sit back on the command line again. This does actually bite us a bit because a lot of the exam syllabuses are still written for doing console I/O as their examples. So we can't be used for certain exam boards because even though we have the right programming concepts, we've got if statements, we've got loops, we've got all object relations, all the things that you might want to teach. If their assessment is very heavily based on, okay, ask the user for a number and then do this with the number, then they're not really going to find a lot of joy in using Greenfoot for it. They are better off with another system. So that's a bit of a shame. We try and sort of, talk to exam boards and convince them to sort of accept some of the more interesting examples. As you get onto things like A-level, doing projects, it tends to be less of a problem because you've got a wider scope. But it's when you sort of have to do even paper-based exams, still coding on paper. Greenfoot doesn't help prepare them very well for that. So the first line of code we write is this move statement. And so the nice thing about doing that is it has an effect. The very first thing you do in Greenfoot is you say move, and then you put a crab in the world, and it runs across the screen. So something happens immediately. And that's a really sort of useful thing, a sort of great motivator. One classic way of teaching programming is, okay, the most fundamental concept in programming is the variable. So we'll declare int x, and now we'll say x equals 5, and then we'll print out the value of x, and it is 5. And okay, we want to teach variables, but they don't actually have to be the first thing. Why not teach something with a side effect that actually does something, and go on from there, actually sort of have something responding. The more feedback they get and the more that they can see what they're doing is affecting something, then that's definitely better. Whereas just sort of manipulating hidden state of the sort of machine, like variables or whatever, it's less engaging. You want something with a very visual feedback, and that's one of the motivations of Greenfoot. What you do can be seen on the screen, not sort of buried away in a concept that you haven't really got your head around yet. We also have a fairly high level of abstraction. We say move, and you move 4 units in the direction you're facing. Then we do have another method, set location, which can take an x and a y coordinate. And so you can technically write move using set location, and then it's get x plus 4 times math times cos of get direction, and then the same for sine for the y direction. We don't do that because they don't all necessarily understand trigonometry. Depending on their age, they might not have covered it. They maybe don't like maths, they don't really get it. By abstracting to this higher level of, we'll just move, they can get that. Move 4 directions in the direction I'm facing. We don't introduce an artificial dependency on trigonometry. We don't really want to depend on trigonometry. We're teaching them programming. They can learn maths in maths class. If they want to use Greenfoot to teach trigonometry, great. But, you know, this is computing. We don't have to depend on maths, so why do so? Just keep it nice and simple. Just say move. That will be fine. We also can get away sometimes with using concepts that sort of sneak past them without really noticing. So that Greenfoot.is key down, we would recognize that that is a static method of the Greenfoot class. None of them ever noticed that. Nobody in all the workshops I've done has ever said, why is it called Greenfoot and why has it got a dot in the middle and what's that mean? You know, they just accept, okay, Greenfoot.is key down is the method name, and they just type it, and that's fine. And that's a small lie, okay, because, you know, it's not really one method name, it's a static method of a class, but that's fine. It's like the third line of code they're writing. You know, you don't have to sort of complicate it up front. You can just whiz past some of the slight rough edges and come back to them later. And then later when you say this is a static method, that's what the Greenfoot, that's why it's got Greenfoot dot in the name, then it makes sense. But it's okay not to make perfect sense up front. So I've talked a little bit about Save the World and how that provides a useful example of object creation. So one other thing we have in Greenfoot, there's a share button. That was the button in the top right of the system. And the motivation there was, okay, you do coding, you know, you go to school or whatever, you do some programming, you come home and you say, wow, I made this really cool thing today. It's like, oh, well, can you show me? Well, no, it's on the sort of school systems, and school systems tend to be a bit locked down. You compare that to something like art. You know, I drew a nice picture today. Where is it? Pull out your bag, you know, here it is. So our motivation, especially back in about, when did we make the site, 2007 or so, you know, haven't really got sort of so many kids with laptops. Okay, let's make a place for them to put up their stuff and share it with the world. So we have a website where you can basically create an account for free, you upload your scenario, and it's playable online. So Java playable online, we used applets. Makes a lot of sense. But the past 2 years have not been kind to us and to applets, so it is a real pain these days, and I think very sort of slowly our website will fade a bit from view. This whole security aspect has damaged, you know, Java in a lot of people's eyes. A lot of browsers just turn off Java by default, so the website's a bit less accessible for everybody. And things like signing the applets is not really a solution for us because, you know, we can't ask every teenager who's uploading to sort of make their own developer account and sign it. And even then, the fact that some random teenager from Nottingham has signed their applet doesn't mean a lot to you in terms of running it. And we can't sign all their applets because, you know, that's not the point of the system. So that's one feature that unfortunately sort of the Java ecosystem is not working so well for us now, being able to play online. So there's a whole bunch of other systems around the place, so there's a few listed up here, there's lots more besides. One I just wanted to quickly demonstrate was Scratch. How many of you have seen Scratch, just out of interest? Okay, so about sort of half the room. So for the other half, just to give you an idea. So this is Scratch, so obviously a lot of these systems have similar ideas, you know. You have some sort of, I think Scratch calls it a stage. Everyone has to have their own name for it, because otherwise it would be too simple. Us included. So over here we've got a stage. I think these are sprites in Scratch, not actors. And what you have over on this side is a bunch of commands. But they're not entered as sort of classic text programming way. These are what Scratch calls blocks. So you can just, this is sort of like a menu of blocks, sort of like a recipe book thing. And you just drag them out of here onto your actual code here in the middle, and just clicking one executes it. So that will run across the screen. You then have various loop constructs here. This is the while true loop. Drop that in, and now if I run that, it just runs across the screen forever after. And if I go back and find a turn block and put that in there, then actually without even restarting, it will now sort of forever turn in a circle. And so Scratch is very interesting for several reasons. It's more accessible to younger age groups, so it's designed for younger age groups than Greenfoot. They don't have to do so much typing themselves. You know, you just sort of drag this thing across and click it, and it works. So it's kind of even a much simpler level than Greenfoot is. And what's really nice about it is there's not really syntax as such. There's not really a concept of a syntax error. Either the blocks are snapped together or they're not. You know, there's no sort of missing curly brackets or half-built forever loops. You know, this is a forever loop. The only question is there something in it or not? So they managed to avoid a lot of the sort of syntax problems in teaching. And that's partly what helps them get down to a younger age group. If you try and do Greenfoot with younger age groups, it's just too much. Trying to juggle all the syntax is enough of a battle without trying to understand what the code does and actually put it all together. So with Greenfoot, we usually say 14 upwards, but it varies a bit. Some people use it with younger age groups down to about 11 or so, but really definitely below that you can't go sort of with Greenfoot, whereas Scratch people often use from ages 5 or 6 upwards. So there's sort of, you know, they're targeting different ages. You've got sort of Scratch, you know, for the younger age and Greenfoot higher up. Yes? Yes. Okay, so just to repeat that for everyone, so the thing about Greenfoot is all that you have to type essentially is, you know, you're typing English keywords for Java and things like that. The nice thing about Scratch is that you can internationalize it by basically just, you know, translating the words in the blocks, but it doesn't really change the system at all. So you don't have to, you know, build a new parser or anything like that. So Scratch can be internationalized much more easily than sort of text-based programming languages, and that helps, as you say, especially at a young age group where not everyone is speaking English. The further sort of you go in programming, the more likely it is that you just sort of have to learn, you know, English at some point. But if you're trying to do 5 to 10-year-olds, that's, you know, it's a different ball game. You're not trying to teach them to be professional developers. You're trying to teach them some of the concepts. So being able to easily translate this is another bonus of this sort of system of Scratch. So that was Scratch. As like I said, there's no real syntax errors because there's not sort of syntax as such, and it's even easier to get started. You don't have to type move, you just drag the move block across and click on it. So, you know, it's even simpler still, but you're still doing algorithms. You know, a way to avoid text-based programming in the past was you build things like flowcharts or sort of, you know, boxes and arrows and things like that, and it was never quite right. The nice thing about Scratch is you're still writing what we all recognize as code. You're just writing it in an easier sort of, you know, format. The disadvantage of Scratch is you do drag and drop the blocks. There's no particular keyboard control for inserting them, and you have to drag and drop a lot of blocks. So if you want to create a more complicated expression, so let's say you wanted to do that, okay, sort of more trigonometry-based example. So you could then, you know, introduce this block. So what do we need to change x by? Well, we need to form an expression. So the expression is some number times the cosine, so you now have to drag in the times block and fill in the left-hand bit there to be 5 or whatever, and then you have to drag in the cosine block, which is here, but you change the operator to cosine, and then what we want to take the cosine of is our current direction, which, where does that live? This is also a slight awkwardness with Scratch. You can't quite remember where everything lives. There we go. This one here, and then we change that to direction. Okay, and I could have written that in Java, you know, just like that, as you probably could have if you wanted to type it out. And so trying to form these sort of more complicated expressions, every time you want a plus or a times, you've got to drag in a new block to sort of, you know, make that times or plus. It gets very fiddly to construct expressions. And although Scratch is quite nice when you've got sort of this much code on the screen, as soon as it gets taller than this, it's very difficult to navigate, especially if you've got sort of lots of these blocks hanging around. So our sort of observation about Scratch is, although I think it's very good and we like it very much, that it kind of tops out too easily. You know, you get too frustrated with the dragging. It's really nice, the syntax bit, but then it's just a bit too awkward to manipulate. So what we're looking at is trying to sit somewhere between the two. So we want to come down from Greenfoot towards Scratch because it's got a lot of good ideas, but we want to come up a bit from Scratch towards Greenfoot and try and make it a bit more usable and sort of be able to carry the idea on further. So the next major project, which I'm working on at the moment, is basically Greenfoot 3, our next major edition. We're going to include a new language along the lines of sort of the syntax editing of Scratch, but then sort of it's effectively the Java language, so trying to sort of manipulate Java through a Scratch-like editor. And I decided to try and brave a very quick demo of our prototype even though it is literally a prototype. I'm running out of my Eclipse installation here, and it may well fall over at any second, but we'll see how it goes. You're all programmers, right? You understand what prototype really means. I wrote code on it yesterday. So if we go for here, so we'll still include Java. We're not taking out anything. We're just adding a new language that you can use inside the environment. The interactions, the methods, the whole API will all be the same. We're just trying to provide a new editor. And although we say new language, it's Java bent very slightly to fit with the new editing style, essentially. But you would recognize it as Java. So if I'm now here and I load up the editor, then I get something, because we've already got this scope highlighting, it looks relatively similar to what we have already. We've still got these sort of colored outlines, but this time they're not inferred from sort of the text that you've written. This time they are actually sort of graphical elements, more like in Scratch. So if I want to change the name of the class here, it's just a text field that I can sort of manipulate rather than being part of the code. I can't change the class word there because it's just, a fixed element. So it looks like Java, but only certain bits of it are editable. So if I then want to write the same code in this editor, the one thing we've added to try and make it more amenable to editing is you've got what we call, what are we calling it? We've got some names, frame cursor or something to that effect. So basically we've got a sort of horizontal cursor that sits between lines that responds to keyboard shortcuts to create code, so that rather than having to drag all the time, if I just press C here for method call, I can then type move, put in my parameter. As I say, we now compile automatically. I go back here, then I get the same behavior, but I'm in this new editor. So if I then want to write, for example, the turn command, then I also do a turn, put my crab back in, then I get it running around in circles. But the real benefit comes from the syntax structure. So when you write an if, you don't want to have to write the whole thing. If you just press I here, then you just get the structure automatically for you. So it's saying syntax error. It's a bit too eager. Again, it's a prototype because we haven't even written anything yet. But we can write exactly the same code as we already did. So that's an experimental sort of bracket matching thing. And what do we want to do when the right key is pressed? We want to turn, but because these are now actual blocks, you can just drag the one you want around the place. So you get sort of the Scratch-like dragging and the mouse interaction, but with the sort of added keyboard control to program Java. So now we've got our same behavior, and then, oops, misclicked. So then if we want to take this across, so we want to form a duplicate, just click in there, so I can duplicate my block. I want left, I want -5, then now I go back to here, and I've got my crab with the keyboard control. So we're trying to still have the same principles as we always had, but we're trying to use a new editor that involves less syntax. In this editor, they can't delete a curly bracket because they're not even in there anymore. So we're trying to make it even easier to sort of do coding without making mistakes that just hold you up for no real reason. There's no real learning to be gained from the fact that you deleted a curly bracket and spent half an hour hunting for where the syntax error lay. You just want to get on with the coding. You want to be tackling logical errors. Well, why is my thing not turning when I press the key? It's because the turn is outside the if statement. That's the more sort of interesting learning that we want to engage. Oh, I forgot a semicolon on the end of this line is not so much the thing we want to be teaching them. We want to get to the algorithms and not be hung up on the syntax. That's the idea behind Scratch, and we're trying to borrow it into Greenfoot. So that's sort of where we see things going. It's certainly for us is to sort of try experimenting with different editors, with new ways of interacting with the code, but it is still the same concepts, the same algorithms, and the same sort of language underneath it. So, in summary, there's lots of interesting systems available. I've only shown you a couple. Obviously, I've shown you Greenfoot because that's what I work on. Scratch also, I think, is very nice. A lot of the other systems around, there's Alice, which is somewhere sort of between the two of them as well. Things like Snap is kind of quite similar to Scratch. There's things like App Inventor, which uses Scratch-like editor to allow you to do development on Android. There's a whole ream of them out there. There's also opportunities for you to get involved, especially with these changes in the UK curriculum. There is a lot of call for sort of, teaching kids to program. There's an organisation called Code Clubs, which you can just Google, and they have materials available for developers to just take the materials and use them to deliver programming clubs in primary school, often after school, sort of 3 till 4, 4 till 5 on a weekday, something like that, where you can go in and get involved with the teacher, do some education. Coder dojos, I think, tend to be at the weekend more, where you sort of come in for, say, sort of teenagers come in for a couple of hours. You're there to sort of help them, guide them in doing their projects. Some of them use Greenfoot, some of them use other systems. There's an organisation called Computing at School who welcome developers to try and sort of help out in different ways, again, by doing events or all sorts of different things. And if you do want to do some Java with them, well, Greenfoot's an option, and we're hoping to build Greenfoot 3 to make something more exciting. We're continuing to develop it, and we just got a session accepted at Java 1 where we'll be doing a demo of where we're up to at that point. So if you happen to be at Java 1 come September, then you can check by the session and see how the prototype's doing and see if it doesn't fall over. Okay, so thank you very much for listening. If you've got any questions, I think I've got about 1 minute left, or not really any time left. Okay, catch me afterwards if you want to ask any more questions. But thank you very much for coming.